Howdy! This is your friendly neighborhood physics teacher here, and we're going to talk about light this week. We're going to see how light reflects, refracts, diffracts, all that fun stuff. But before we get into more of that stuff, we need to know what light is. Light is such a broad spectrum. You'll get the joke in a minute, I promise. But light is such a big idea. We have to break it down to what different types of light is out there. And I thought this joke was really good. And if you ever see Miss Verona drinking another Red Bull, tell her no. But this is kind of funny. So this young physics student comes into the local corner store and goes, "Do you sell ultraviolet blue? A bull?" He's like, "What? Excuse me? What about regular violet bull? What? No. Blue bull? No. Green bull? Yellow bull? Orange bull? No, no, no." At this point in time, he's probably getting really tired of the kid. It's like, "Rats. I'll just take the Red Bull." He goes, "I was hoping for something a little more high energy. At least it isn't infrared bull." So he's talking about the different colors of the spectrum. You go from red to pretty much RGB, which I'll post a video that Miss Verona wants me to post just to prove that there's no indigo in the rainbow. But we'll get to that. I keep jumping ahead of myself. So light, what is it? We think about light as just what we can see, what we see in the visible light, but light is so much more in the spectrum. It's the electromagnetic spectrum, to be completely sure. So how would you describe that? How would you describe light to a blind person? And you got to think about that. It's, you talk about color, you talk about brightness, you talk about dimness. And it's a really hard concept to think about, describing light. I mean, you can describe texture. If someone said, sit there and describe, I have a Pikachu stuffed animal sitting at my desk right now. You sit there and describe like the texture and how it's made and stuff. You could do that because it's tangible. But light's not a tangible thing. And it's just a hard thing to describe what light is. And then when you get into the spectrum of different lights that you can't even see, it gets kind of complicated. So light is, and this is where it's the electromagnetic waves. They're made up of two different forms, and pretty much the magnetic field and the electric field interact to make this wave, and they go at a 90-degree angle from each other. You can see that. So right now we have the electrical field that's going up and down, and you have the magnetic field that's going side to side, and those interactions make the different electromagnetic spectrum. Kind of move like that. Looks like a really funky snake. And it is basically two transverse waves that are kind of combined. And just a reminder, transverse, if you sit there, it's the basic waves you draw. If I say, here, draw a wave, that's the wave you're going to end up drawing. And it still has wavelength, it still has amplitude, still has crest, still has troph, still has your undisturbed state or your equilibrium state or your zero state. There's so many states that little center line is called. And you still have the movement of energy. So just a reminder of that. I know it's been like 2 weeks since we talked about that. Now, sound is what we talked about last week, and just kind of describing the difference between light waves and sound waves. Well, light waves are the electromagnetic waves. Sound waves are mechanical waves. Think about the word mechanics. You actually have to have something to interact to make it work. Your electromagnetic is just a field. Light can work in space and sound can't. So light is transverse. Sound is longitudinal. Transverse is that up and down motion we just saw. Transverse, remember, is that compressing and refracting, kind of like a accordion. And then this is what I was saying, that light doesn't require mediums. Medium is anything like that's a solid, a liquid, a gas. Your light, that stuff actually gets in light's way. It's like, move out of the way, poof. Your Sound needs those. That's why sound moves faster through solid and slower through gas, which again, everyone's little brain's like, what? Hold on, we talk in a gaseous state. Yeah, but that's why you sit there and scream. I can't sit here and scream at you and you get this lecture. We actually have to use a little bit of technology to get this. Versus light, honestly, if there's nothing, like there's no solids obstructing me at all, I could probably sit there and Morse code you the information, if you knew Morse code, and you would get the information. Again, as long as there's no solids, liquids, or gases affecting the movement of the light. We live on Earth, so there's a lot of that. So your electromagnetic spectrum is this huge breakdown of all the different frequencies of waves. And we can kind of classify all this different. And the thing is how it travels through a vacuum. That's the most basic state, is vacuum, when there's no gas, no liquids, no solids to kind of slow it down. Now our biggest ones are radio waves. Yes, radio waves are light waves. I know you're like, but when I push the play button, sound comes out. It starts as light in the mix of things in that little box through magic. No, science, joking. It produces the sound. So that's where there's a transfer of energy. Oh, look, we're going back to Unit 1. So transfer of energy going from light to sound. So you have radio waves. Then you get into microwaves. Yes, that's the thing that you've been cooking most of your food in, at least I have. Then you get into infrared. Yes, that's the fancy little goggles. Visible, that's the world we live in. Ultraviolet, X-rays, and gamma rays. And as you can see, the little squiggles, radio waves are huge. Gamma rays, but we'll talk about each version. And trying to get you a size reference. So your radio waves are like the size of Mount Everest. They're that big. Skyscrapers. And then you start getting into, even microwaves. Microwaves are a form of radio waves. Like, it's one of those that it kind of blends. Like, it's not really a radio wave, but it's a microwave. So they still kind of, that's like where it kind of blends. Microwaves are its own wave, but it's really not. It's one of those moments. And so those, still radio waves size of human. Radio waves has the biggest range of size, according to how far it needs to go. So microwaves gets your finger. You get into the infrared, which gets into pit head of a nail and dust. Visible is the size of bacteria. You get into some ultraviolet, bacteria, viruses, X-rays, virus, and atoms. And then you get into your gamma rays, which gets on the atomic level. And so first thing we're going to talk about is radio waves. Again, radio waves is the biggest range of waves we have. So they have the lowest frequencies, but they have the longest wavelengths. Remember, frequency is how frequent the wavelength happens. So since they're so big, it takes a minute. It's like, wavelength. So it takes a minute to get through the whole entire wave because they're so big. And the easiest example of that is your FM and AM radios waves. If you could see, we only see in the visible light. If you could see in radio waves, you'd be bombarded with so much information, you couldn't see anything. You couldn't see your computer in front of you or your phone in front of you, whatever you're watching this, because of how much radio waves are attacking us constantly. And again, radio waves are not sound waves. They get transferred into sound waves. So actually there's radio waves going from the satellite to your phone so you can watch this. And but the sorry, lost train of thought. But then again, in your phone gets transferred into sound waves. So there's a transfer of energy there. Yep, transfer of energy. Woohoo! So now microwaves. So microwaves, like I said, are a type of radio wave. And they're also used for cooking and communication. Your phone uses microwaves. Yes, your phone, when if you remember your mother telling you not to stand in front of the microwave because you'll get hurt. The same thing you put up against your head, or you fall asleep at night talking to your best friend, produces microwaves. These things are lovely things that we're attached to now because of we're being quarantined, can hurt us. Now, the studies they did, they literally stuck the phone, like taped the phone to the rat's head for god awful amount of hours. Yes, they produced brain cancer, but please don't tape the phone to your head. But the next time, our young ladies think about sticking the phone in your bra, the next time, young men think about sticking the phone in your front pocket, those are radio waves attacking very important body functions there. They've actually have said that it's caused breast cancer. It actually says it's called testicular cancer, leaving your phone close to those body parts. And also it has known to cause brain cancer, sitting there leaving the phone on your head. It's now, again, you have to do that like all the time, every day, consistently, forever and ever. But just think about that the next time you realize how attached to your phone you are. And I want to know how many people, as soon as I said that, took the phone out of the bra, took the phone out of the pants, took the phone away from their head, put it across the room. But yeah, no, truly, they're not the best thing. They're not the best in the West. With the microwaves, there's a reason why there is a metal grate separating you and the microwave. And so those parts can't come and cook you. So microwaves, okay, I know this is a play microwave, but usually there's a metal grate right here. And it's to deter the microwaves to get out. So radar. So we're still dealing with a form of microwave, but radios that's detecting and ranging is a microwave that uses to locate, calculating distance and monitoring and your automotive speed. And the reason I put the radar in is because most of y'all know I'm a meteorologist, and this is what we use to track storms. We send out microwaves, and it hits the clouds. We can see how big the cloud is. We can actually see if there is rotation, how the cloud is rotating, which direction. So I used radar a lot in my undergraduate research, tracking lightning and stuff. And so I'm very familiar with radar. Now, infrared. So infrared cannot be seen, but it can be felt as heat. So warm objects give off more infrared than cooler objects. So hunters use this. Building inspectors are actually starting to use infrared guns to see where the hot and cold spots are in your house. So you can see, this window's not, keeping heat in. It's letting heat out or something. So there's other ways to using than hunting. Most people jump to hunting or military for infrared, but it's becoming more and more accessible to the, I guess, common person. You can go to Academy and get it, and it only costs maybe $100 now, which it used to be a pretty penny before. And you can see how, a cold-blooded animal would not necessarily give off heat as much as we would. Visible light. The world we live in. Think about look how little the world we live in. We don't live in any of this world. We feel it, we see it, we interact with it. We don't really see it, so we interact with everything. But this is the only part we can see. This is what we can see. So this is the Roy G. Biv of the world, the rainbow, which is red, orange, yellow, green, blue, violet. You did not hear me say indigo. Indigo is not in the rainbow. They just did Roy G. Biv because it sounds better if you actually spell it out. The I is lowercase because it's not a thing. Roy G. Biv. There is no indigo. And yes, I understand. You see that little, I forgot my thing was touchscreen. Yes, you're like, well, look at the indigo. So no. We understand the color exists if you sit there and blend it. We understand the color exists, but it's not a true wavelength. It's not a true part of the rainbow. Now, refraction. Now that's different from reflection. Refraction and reflection are two different things. So refraction is when you pretty much turn light into a prism. So you have white light that goes in. The prism refracts, so spreads out the different wavelengths. So red moves a whole lot faster than your purple and your blue. So it actually, according to its speed, will spread out. And that's how a prism produces a rainbow just by using white light. White light is all the colors. So white light is consistent of all the colors. Black would be like think about like a black hole is the lack of color. And now that's opposite than you're thinking like in your art class. Um, so art class, you're like, no, white can only be white. And if you want to make black, you blend all the colors. Well, that's different from pigments. It's completely different from light. Pigment, light, two different things. And your blue light refracts more because it's moving a whole lot slower than your red light. And so that's how you're able to spread it out and produce that rainbow. I had to, sorry. So how does this differ from diffraction? So we've talked about refraction. So how's this different from diffraction? Oh, so diffraction is actually kind of the opposite. It's when you have the things combine. So refraction is when it spreads out, or refraction is when it spreads out. Reflection is just when it bounces off at an equal angle, and then diffraction is when it kind of converges together. So it does the exact opposite. But we'll get to that dealing with lenses more next week. So now the next part is your ultraviolet rays. Basically now we're getting into enough energy to start killing living cells. And this is basically when you go suntan. And we need these. We need the sun. If you haven't stepped outside today, go do it. It's a pretty day. But we need the sun. We just don't need too much of it. It's kind of like we need heat. You know, we talked about in energy, if you get like a serious burn, is because your cells can't handle that much energy. It's the same thing. That's the same thing with a sunburn. You've taken up all this ultraviolet energy, and your cells are just like, I can't take it anymore, and they get sunburned. You're just killing that first layer of skin. You get first degree, second degree, third degree. It's just how deep in the skin level you go when you kill those cells. So it's something we need that energy, but we just need a little bit of it. We don't need a lot of it. And that ozone layer is what protects us from the sun's rays. So that big thing when like hairspray is killing the ozone layer, it's because they're like, oh, we're killing our protection from the sun that we need, but we don't need too much of it. So, it's the, too much is a good thing type of thing. We're going with that aspect with the ultraviolet rays. And see, just a little bit. X-rays. So everyone's, X-rays. Reason they use X-rays because they're small enough to pass through like the tissue, the soft, squishy parts of our bodies, and they reflect off of the hard parts of our bodies, which would be the bones. Now you can sit there and change your X-rays to. I know when I was in college, I had some intestinal issues, and they were able to modify the X-ray so they could actually X-ray my intestines and see like, oh, you have a blockage here. And so that was, your intestines are your squishy part, but then you can sit there and intensify it a little bit. That's why you see soft rays and hard X-rays, for the soft materials versus the hard materials. Now, X-rays still hurt. I mean, if ultraviolet, of course, X-rays are going to still hurt. If you're a female, they sit there, you have to sit there and sign, I am not pregnant, to get a X-ray anywhere. And then they lay this big heavy thing on you. To protect, your reproductive organs, because again, you can mess that up. And you also, if you've ever like broken something consistently, you have to sit there and say how many times you've been X-rayed in a year, and there's like a limit because it can hurt your soft parts of your body because it's killing your body. It's again, you're taking so much energy in that your body's like, nope, can't handle. Kind of like with the microwaves. I didn't talk about this. I'm going to backtrack to microwaves real fast. I realize I haven't talked about this. And how microwaves work is it heats from the inside out. That's why something can be on the cold, but like hot in the inside, or even vice versa sometimes. But it's heating up from the inside out. It's making the water molecules in the object boil and getting heat out that way. I forgot to talk about that with microwaves. So X-rays. You can actually see, different ways. I believe this is one of Miss Verona's children. And so you can see all the lovely teeth coming in. So gamma rays. So gamma rays are the highest amount of energy, so they're the smallest wavelength, highest frequency. And this is, radioactive material emit gamma rays, and it's also used to treat cancer. The reason it is used to treat cancer is because you can sit there and focus on, okay, so your cancer, let's say, is you have a blob in your leg that's like cancerous, a tumor in your leg that's cancerous. It can pinpoint that area, and you just shoot a lot of gamma rays in that area. The issue is you can't go, hey, gamma ray, you see the bad cell? Go kill the bad cell. And he just goes, kills the bad cell. It kills all the cells. That's what makes the people that have cancer so sick, is because you're not just killing bad cells, you're killing good cells also. But you try to pinpoint, you're like, okay, I'm going to pinpoint this area. And that's where it gets, when you actually start having cancer in, organs, you're not just killing the bad cells, you're killing the good cells also. You can't just sit there and give the gamma rays a roadmap and say, only get this, it's a, bloodhound, sniff out these bad cells. It's, it kills good and bad. And so, yes, it's useful, but it's dangerous. And that's why people get really, really sick when they're on, radioactive treatments. And then just radioactive material emits gamma rays. You'll be amazed when we get into nuclear, which would be our next unit we talk about after we get through with mirrors and lenses. What actually produces gamma rays? You'd be amazed. There used to be like Tupperware, or not Tupperware, but like plates that just produce radiation just because of the material they're used. And so you probably are slightly radioactive, not on the way of turning into the Hulk radioactive. So no, we have no Hulk or She-Hulk issues here. But you do get a little bit of radiation. So speed of light. You've actually seen this number before when we talked about just waves in general. So speed of light is represented with a c, which is technically 2.99792458 times 10 to the 8th meters per second in a vacuum. We don't live in a vacuum. And guess what? We just round that up to 3 because we don't want to deal with that many decimals there. And the speed of light, it moves fastest, unlike sound, who moves fastest through solid and liquid than gas and doesn't work in a vacuum. Light works backward. It moves faster in a vacuum, and then sound, liquid, and then solid. So that's why when you sit there and put a pencil in a glass of water, it looks like your pencil is broken because your speed of light has changed. It has, what's refracted? Woo, new vocabulary. Well, we learned it a minute ago, but it's refracted. And because the light moves faster in gas, moves slower in liquid. Kind of cool, huh? And we just kind of rounded up to 3, and we use it as vacuum and air because when you go from vacuum to air, it only changes just a little bit. It's not enough to really affect, at least the calculations that we plan on doing. And since our lovely country doesn't do work in meters per second, so that's miles per second, if you really want to convert there. So just a couple of things. It's dealing with light or any electromagnetic wave. Your V and your C are interchangeable. So going back to the equation that we learned just about your waves, your V equals frequency times wavelength, or wavelength times frequency, whichever way you want to do it. You just change that C to V, and you got it going on. So it's the exact same equation there. So a little bit of practice. So what is frequency of electromagnetic wave with a wave of 3.5 times 10 to the negative 8 meters? So that would be our wavelength. So it gives us our wavelength, and we're looking for frequency. And we have a constant now, right? So we know our constant, our C, is 3 times 10 to the 8th meters per second. So we have a constant. So we're just going to use our equation C equals wavelength times frequency. And, didn't mean to put an equal there. And so we're going to do 3 times 10 to the 8th equals our wavelength. This is 3.5 times 10 times 10 to the negative 8. And we're looking for our frequency. I did not mean to do that. Frequency. Can I put an F there, please? Frequency. And we need frequency by itself, so we're just going to divide. We're just going to divide. When you put this in your calculator, make sure you put parentheses around both of those. That cancels, and so then you get your frequency to be your 8.57 times 10 to the 15th hertz, because hertz is your frequency. Now, for what is the wavelength of a microwave with a frequency of that? So again, we'll already put an F there. So that is our frequency. Again, our constant is speed of light. So if we use the exact same equation, we're going to do 3 times 10 to the 8th equals, we're looking for wavelength, our 2.99 times 10 to 11. Again, we're going to divide. Or not, because I'm getting too low. 11. Again, make sure you put parentheses. Technology doesn't like me right now. And you get that that is your meters. That is your wavelength. So relationship-wise. So if you're dealing with electromagnetic waves and velocity is constant, so what's the relationship between wavelength and frequency? Hopefully you know this. Do 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 do. If your wavelength goes up and your velocity is constant, frequency has to go down. So that is an, drum roll please. But it goes the other way also with your inverse relationship. Inverse relationship. One goes up, one must come down. So just a couple of things that you're supposed to get. So what happens to the frequency if the wavelength doubles? So if your frequency doubles, or what happens to the frequency if your wavelength doubles? So if your wavelength doubles, your frequency would have to decrease. So it would have to be by 1/2. It would have to decrease by 1/2. There's my pen, 1/2. So frequency of a wave decreases by a factor of 4. What happens to your wavelength? It will increase by a factor of 4. Wave 1 has 3 times the frequency of wave 2. Compare the wavelengths of the two waves. So 3 times the frequency of, so compare the wavelength. So wave 1, so basically if we're looking, so wave, come on pen, please pen. Wave 1 has, not wanting to write all of a sudden. I'm almost done. Let me write. 3 times the frequency. Oh, Lord have mercy. All of a sudden I can't write. Why can't I write? Pen. Okay, we're going to do it this way. 3 times the frequency. Then your wave 2 only has, we're just going to say only has frequency. So again, so if your frequency increases, your wavelength has to decrease. So your wave 1 is going to have a smaller wavelength than wave 2. A wave has a wavelength of 50 centimeters. If the frequency is halved, what is the new wavelength? So your 50, your velocity decreases. So that means your wavelength will have to increase by 2, so just be 100 centimeters. There we go. So relationships are fun. Woohoo! So that's it for the light notes. please jump over to the mirror notes, and we'll continue over there. Hope you have a wonderful day. Bye.